Force concepts. What's a force? I gave you the same definition last year. I said a force is a push or a pull. And then I probably went on a rant last year. I said something like, that's actually not the correct definition. A physicist would say a force is an interaction between two objects when they exchange leptons. Fine. You can always, Matt, dive down to the quantum level and get what's technically the correct explanation. But it gets weird there. So we're always just going to zoom out and we're going to say, a force is a push or a pull. That'll work. Remember that force is a vector. It has direction. It mattered which way was winning and which way was losing. And it was measured in newtons. Also remember, a newton was technically a kilogram meter per second squared, since F equals what, if you look at the units that make that up. Forces are based on interactions between two objects. That means, by the way, if you have an object in outer space, far away by itself, with no planets or gravitational fields anywhere, it's impossible for that object to experience a force. There has to be a second object. That's also why forces come in. You remember that? It's because they are interactions between two objects. Some important forces that we'll study in this course that we saw last year include the following. What did we call the Earth pulling on all objects downwards towards the planet's center? What force was that? Gravity. We called that gravity. And the symbol that I used was a capital F, lowercase g. Who remembers what was another name for the force of gravity? Know now. Who remembers what was another name for the force of gravity? It started with the letter W. Know now. What? Know now. What? Weight. Weight is the force of gravity. Some textbooks then will use a capital W. I don't, just because, believe it or not, W is west, W is watts, and W is work. That's enough W's. I'll use subscripts because that way it's the force of gravity. What was the name of microscopic hills and valleys between an object and a surface that would interlock and prevent or impede sliding? What do we call that? Yeah. And my abbrev was F. And I don't know why I put the FFR. It's really, every other textbook just calls it FF, but I haven't changed that habit. I started out that way for some dumb reason, Grace, when I started teaching physics back in 2003. Still there. It's about the only time I ever write an extra letter when it's not necessary. What was the name given to the surface pushing up on an object, or a wall pushing out on an object? It was also the apparent weight of an object. The normal force, and this is what all of you think of as your weight. You may see some textbooks just use a big capital N, but to me, N is north and N is newtons. I'll use F with a subscripted N. Okay? Good day, good day. Glad you made it. So the normal force is what all of you are feeling right now, and you think that's your weight. All of you lift your feet up off the ground so that you can feel the chair pushing up on you, okay? That's the normal force, but that's what you're used to. You think, oh, that's gravity pulling you down. No. It's the ground keeping you from sinking. If I jumped off of an airplane, mentioned I jumped out of an airplane. When I jumped out of an airplane when I was in free fall, was there gravity acting on me? Yes. Did I still possess weight? Yes, but I felt weightless because there was no normal force. I think I showed you an OK Go video last year where we saw they were doing a plane and putting it into parabolic dives and accelerating at 9.8 meters per second squared down, and they could achieve apparent weightlessness. And in fact, that's what the astronauts on the International Space Station feel. They feel, in fact, if you ever listen to an astronaut on the International Space Station, they'll always use the term microgravity. And that's their way of saying, look, we know gravity is up here. We don't feel it because we don't feel a normal force. Hey, what was the force from a stretched string that was constant throughout the string? Like you're feeling right now? And here's where I have to apologize. Here's probably the worst bit of teaching that I do. I use a T for tension. I should use an F with a subscripted T. Because you're going to find later on this year, capital T means something different. And there's going to be an equation where a capital T that means something different and a T for tension show up in the same equation. And no, they don't cancel. And no, they're not the same thing. And I'm sorry. What was the contact force from an external agent, usually coming from off the page? We said, it might be an invisible leprechaun. I don't care, but something. Remember what we called that force coming from off the page, the mystery force? Yes, it was the applied force. All that was me saying, look, something's applying a force. I don't care what. I'm not going to make up a story for that, but I'll just draw an arrow showing you it's coming from off the page. What did we call the force of resistance from the air opposite to the direction of motion? Ooh, you got the fancy schmancy word. Drag. Good morning, good morning. And I usually called that F air. If you called it F drag, I'd be fine with that as well. The last one was not a force that showed up on our free body diagram, but it was the vector sum or the resultant of all of the forces acting on the object. F what? We have a fancy schmancy word for total. It's actually F equals MA. It was never F equals MA. It was F something equals MA. It was winner minus loser equals something. What? F net. The net force is the combination of all of the vector sums. It never shows up on the free body diagram. All of the subcomponents show up on the free body diagram. F net was what showed up in our equation on the right-hand side. That idea that F net doesn't show up on the free body diagram is also going to be important when we get to circular motion, because when you're moving in a circle, it's the net force that's pushing you in a circle, but F net doesn't show up on that free body diagram either. I went on my big rant last year about Sir Isaac Newton. We said that Isaac Newton described how everything in the universe moved using 3 laws. His first law is often phrased, objects at rest tend to remain at rest, objects in motion tend to remain in motion. Here I wrote, every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Huh? Jack, here's what I said. The only way that you can accelerate an object or change its velocity is to apply an unbalanced outside force. If forces are balanced, what must your acceleration be as a number exactly? 0. Which either means you're at rest if you were at rest, or if you were moving, you're going to keep moving in a straight line at a steady speed. That second one explains outer space. Outer space, if there's no planets around, no gravitational fields around Marcella, you fire your rocket, and then you could turn your rocket off and you can coast. And you'll just keep going until the edge of the universe. Right? The Voyager probes that we've launched out to the edge of the solar system, we gave them enough speed to escape the gravitational field of the sun, and now they're going to coast. And they'll coast until the end of the universe. Or until they hit something, if they keep going, thousands and thousands of light years, maybe there's something in their path, or they'll get captured by some other gravitational field in another galaxy or another solar system. Maybe, but Newton's first. This is often called the law of inertia, because the more difficult it is to change an object's motion, the more inertia that object has. It's pretty easy to change the motion of a feather. It doesn't have much inertia. You can blow on it and you'll change its motion. It's pretty tough to change the inertia of a locomotive. If you blow on a locomotive, I assure you, you're not changing its motion. Or if you are, it's not by anything we can detect. We actually said that inertia and mass were the same thing, and then technically that's wrong because you learned with Einstein, as objects speed up, their mass, their inertia increases. So inertia and mass, Alex, aren't the same thing, but as long as you're not going near the speed of light, they'll be close enough to the same thing that we don't care. So if you want to know how much inertia an object has, what's its mass in kilograms? That's its inertia. Put your pencils down, look up. Newton's second law is the equation. It's the mathematical relationship. It says F equals ma. Actually, it says the net force equals mass times acceleration. By the way, Newton never actually wrote this equation. He was much more interested in acceleration. So he wrote it that way. But he never actually wrote it that way either. He wrote things in terms of momentum. So I should point out that this is the simplified, more convenient in our vocabulary version of Newton's second law. Newton's third law is the action-reaction law. For every action, there is an equal and opposite reaction, which again, to me, is confusing. Mr. Dewick says forces come in. And really, I should say opposite pairs. As an equation, the force of object A on object B is the opposite of the force of object B on object A. F of A on B equals negative F of B on A. So based on that, for example, why would a running athlete, a track athlete, want low mass shoes? So specifically, let's say a 100-meter sprinter. Okay, so you're in the 100-meter sprint, which is probably the oldest athletic event in history. Somewhere, there was an ancestor of ours, a caveman or whatever, who's race you to the water hole. Probably the oldest event. Yeah.
Because since A is F over M, if you make M smaller, that makes acceleration.
Lovely explanation. As M decreases, arrow pointing down is my abbrev for decreases. A increases, arrow pointing up is my abbrev for increases. Ooh, if you were on the International Space Station, would it get hurt to hit in the face by a moving object in 0G?
Sure.
Yes.
Convince me.
But it still has mass.
So?
So the impact is stiffer.
Oh.
So this still has mass. When it hits your face, would its velocity change? Be obvious. When it hits your face, would its velocity change? I'm going to ask you the same question. I'm just going to phrase it differently. When it hits your face, would it accelerate? Decelerate. But would there be an acceleration? Yes?
So, yes.
Yeah. If there's a mass and there's an acceleration, it will apply force. Okay? So, a force with which you might have had some experience is the force of gravity on the Earth, between you and the Earth. By the way, since forces come in pairs, if the Earth is pulling on you, you're also pulling on the Earth. But the Earth's mass is so huge compared to you that the acceleration is basically zero. And the odds are pretty good that on the other side of the planet, there's roughly the same number of people, roughly, and so they roughly cancel out. I point that out. The force of gravity is known as weight. Know now. And it's measured in units of newtons, or in the old system, pounds. How do we measure mass?
Kilogram.
Does anybody know how we measure mass in the imperial system? It's not pounds. Pounds is actually correctly called a measure of force. When you say your weight in pounds, that's a correct statement. When you say your weight in kilograms, that's an incorrect statement. If you say your mass in kilograms, that's a correct statement, but you should be saying your weight in newtons. Okay, so the imperial unit for mass is slugs. And congratulations to none of you that bothered reading ahead. Which, again, you've never heard of, and again, is why the imperial system is such a stupid system. Wish the US would go metric already. So, to relate mass to force, if we're trying to calculate the force of gravity, we need to know the number of newtons of force per kilogram of matter. Here's a new phrase for you. Paige, we call this the gravitational field strength. We said the force of gravity was equal to, get the obvious one, mg, which means little g is equal to the force of gravity divided by the mass. This is the gravitational field strength of a planet. Do you know what Earth's gravitational field strength is? 9.8. But also, because this is force divided by mass, Emma, this is also an acceleration, yes? The reason objects in free fall accelerate at 9.8 meters per second squared is because Earth's gravitational field strength is 9.8 newtons of force on every kilogram. It's a different way to think of the same concept. So let me give you an illustration. Let me pause the video for a second. So example 2 says, find the weight of a 10 kilogram object on the Earth or on the moon. Okay, what's another word for weight? Force of gravity. Or another phrase for weight, force of gravity. So Fg equals mg Earth, and Fg equals mg Moon. Owen, in this question, what's the mass? What's g on the Earth? We don't include the negative here. We're just getting the magnitude. In your head, what's 10 times 9.8? Good. So a 10 kilogram mass, that spring scale that I just showed you, if I had a 10 kilogram mass on there, it would be pulling down with 98 newtons of force on my arm. What's the moon's acceleration due to gravity? I stuck it up here in the paragraph. It's about 1.6. So it's going to be 10 times 1.6. Owen, that's your cue. 16 newtons. So does the object have less mass on the moon? No. Less weight? Yes. And there's the answer a little bit to your question then. So you would be able to lift up more than you were used to on Mars, let's say. It's a trickier question because you'd almost certainly be wearing a spacesuit. Spacesuits are terribly difficult to wear. Basically, you're in a pressurized suit in a vacuum. Okay? So what the spacesuit wants to do, it wants your hands to go full out like this, because if you inflate a balloon, it wants to be as big as possible, and it wants your arms to go out like this. So anytime you're doing any kind of fine work, you're having to, like you're squeezing a tennis ball, you're having to squeeze your fingers in to do any kind of fine work, and same with your arms. Chris Hadfield, his first spacewalk, I think, was on the space shuttle, and he said he was out there for a couple hours. When he came back in, they removed the spacesuit, and he said he just curled up into a fetal ball in 0G and floated there for half an hour shivering. Like he was wiped. He had nothing left. It's exhausting. And so if you watch, for example, the movie The Martian, they had mythical, much better spacesuits that Matt Damon was able to move around pretty easily. We don't have that technology yet. Still working on it. Example 3. Oh, we get to vote. If the force of gravity acts on an object, then that object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. If the force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. Once again, we're going to vote. Once again, high, hold your hand up is how sure you are of the answer. So, who says obviously remains at rest, Mr. Dewick? A. Really? Who says, no, moves at a constant speed? Who says, clearly Mr. Duke is going to accelerate in the direction of gravity? Who says, oh, really? Convince me. So if I gave this to you as a using principles of physics right to explain question, and I won't because it's here, I think the easiest would be to give an example of how each one can be true. Give me an example of how an object can be feeling gravity but remain at rest. Sure. Us. Sure. I'd take that as well. Sitting in a chair. Can you give me an example of how it's possible for an object to be feeling gravity but moving at a constant speed? Yeah. Right? When you stop accelerating when you're in free fall, mentioned I jumped off an airplane. What about C? Yeah. If you didn't include the phrase terminal velocity, I don't think I'd be that nitpicky. I'd probably give you credit on a test, but in our notes, you'll be accelerating until you hit terminal velocity. Sure. So, D. Yeah, I'd take that. That's a good answer. So Newton's first law says, if we have balanced forces, objects at rest remain at rest and objects in motion remain at, you know what? If we have balanced forces, A equals 0. If we have unbalanced forces, Grace, A cannot be 0. It's impossible. So F net, or the sum, this symbol here is the sum of all of the forces. We have this, F net equals MA. So last year, Jordan, when I was doing winner minus loser equals MA, really what I was saying is winner minus loser, the vector sum of all of your forces is the net force. I just wasn't calling it that, but that's what we were doing. A little note, by the way, newtons per kilogram and meters per second squared must be the same thing, because A equals F over m. Well, acceleration is meters per second squared. We defined it that way last year, but it's also force, newtons per kilogram. So again, another term for the acceleration due to gravity is gravitational field strength. Those are interchangeable, measured in newtons per kilogram. So there may be some times in your future when I tell you a planet has a gravitational field strength of 12 newtons per kilogram. What I've just also told you is the acceleration in free fall is 12 meters per second squared. Mr. Duick, yeah, how do we know ahead of time what the gravitational field strength of planets are? Because surely we had to know what the moon's was before we went there. Otherwise, we wouldn't know how strong to build the rockets to land there. Good question. I hope to get to that in our last couple of lessons this quarter. I really want to get to gravity and orbits with you folks. So we talked about net force. Example 4 says, find the unbalanced or net resultant force in each case. Just so we have some, let's put a compass rose, north, east, south, west, and that way all of our answers look the same. What's the net force on A, magnitude and direction? I'll give you a hint. 2 newtons at which way? East. Jack, what's the net force on B? 3.7?
3.7.
That's what you said, right?
I said 2.7.
No. Oh, I gave you an out, dude. Wow. I threw you the lifeline and you just tossed it back at me. No, that rope's a little scratchy, Mr. Dewitt. Give me a different rope. Okay. 3.7 direction.
So
Good. Ooh, harsh, a little trickier. What's the net force in C? Yep. Direction? Yep. Ooh, Percy, what's the net force in D? With authority and confidence in your voice. Better yet, while looking at Jack, with authority and confidence in your voice. There you go. Ooh, Kai, what's the north-south net force in part E? So who cares? Now here's what that means. That means either this isn't moving up or down, north or south at all, or if it is moving north or south, it's moving in that direction, that component at a constant velocity, not accelerating. I don't know which, but I know one of those must be true. What's the net force? Ooh. How could I calculate the net force? More specific, in this specific example, what would the equation be to calculate the net force? I heard somebody say it. Y minus X newtons south. What if they were at angles? Well, I could try adding or subtracting by tip to tail, or how do I subtract vector? Probably what we would choose to do is break it into components, though it'd be easier. And we'll get there. So to solve force problems, we're going to use what we call the free body diagram. We're going to draw an arrow for each force that acts on the object. F net is never going to show up on my FBD, my free body diagram. We're going to label the arrows. We're going to try and draw them roughly to scale. Paige, what do I mean by roughly to scale? If they're the same size, I'll eyeball it, try and make them the same size. If I know one is bigger, I'll eyeball it and make sure one looks bigger. Okay? My friend who created these notes, it's actually a prof from Kwantlen, whose notes that I kind of have modified. He also puts acceleration and velocity vectors, but he draws them differently. So he uses a squiggly line for acceleration, and he uses a dotted line for velocity. I keep my free body diagrams pristine. I only put forces on them. It's just me being me. So if you want to add extra stuff, you can. I'm not going to take marks off. Come up with your own system that works. So we're going to use it to write an algebraic net force equation like we did in 4F, which, yeah, we called winner minus loser, but we're going to get a little more complicated this year, but not much. Our net force equation will be derived by using a tug-of-war analogy. We're going to go, you remembered it, winner minus loser equals, I'm going to write F net, and then I'm going to cross it out, MA, because that's what F net is. So we'll go winner minus loser Jack equals MA, but the reason we're going winner minus loser equals MA is because winner minus loser is the net force, and F net equals MA. We're just combining two little steps in one. This will allow us to avoid having to decide ahead of time which way is positive, which way is negative. Positive is going to be whatever makes the math nicer. In Unit 1 that we just finished, down was always negative. In dynamics, especially when there's more than one mass moving in different directions, up is what makes the math nice. Positive what makes the math nice. Example 5. Turn the page. A 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. A says draw a free body diagram. Okay, there's the rock. What are the forces acting on it? Get the obvious one. And remember, I did kind of a routine, a systematic approach last year because students always want to rush to the complicated one, the weird force. And I said to you, look, do the ones that you know. And often the weird force, it'll become obvious by the end. You'll be like, oh, it's got to be this. So gravity. What else? What do we call the force from a cable? Tension. Which way? Up. Bigger, smaller, or the same size as gravity? And how do I know? Why do you know? Which way are we accelerating? Upwards. Which way must the larger unbalanced force be? Upwards. So I'll exaggerate it in my diagram. There's tension. Okay. B says compare the forces that act on the object. I did in my free body diagram. I figured out which one is bigger. C says write an equation. Who's winning?
Tension minus gravity.
F net, but I'm going to say since F net is ma, we can go tension minus gravity equals ma. What does D want me to find? How would I get the tension by itself? Oh, I like that. So you're telling me that tension is going to be mg plus ma or ma plus mg, adding order doesn't matter. You could factor out the m's, but it's not going to do you much good here because did I give you the mass? Do you see kilograms anywhere? Did I give you the mass? What did I give you? I heard somebody say the magic phrase. I gave you mg. So my equation is going to be this. 2,000 plus, not 2,000 times 9.8. I did that already. That's mg. Oh, what's A? How can I figure out the mass if I know the weight? Divide by 9.8. Okay. Last year on your green sheet, I did tell you that the force of gravity was equal to weight, was equal to mg. I don't think I put that on your yellow formula sheet. You can add it to your purple one if you need to as kind of a hint. But yeah, it's going to be 2,000 plus whatever 2,000 divided by 9.8 times 3 is. What do you get? 2612. Anybody else? I'll go 2,610. I'll just go to 3 sig figs because that's a habit I have. Is that wrong? Okay. So tension, 2,610. How big was the force of gravity? How big was mg? Exactly as a number? 2,000. Okay. We're going to vote again. Example 6. Is it correct to say that if the rock in example 5 is moving upwards, then the string tension must always be bigger than the weight of the rock? Is it correct to say that this answer must always be bigger than 2,000 if we are moving upwards? True or false? We're going to vote. How high you hold your hand up is how sure you are of the answer. So if we are moving upwards, is it correct to say that the string tension will always be bigger than mg? Who says, yeah, that's absolutely correct. It has to be bigger than mg because you're adding. I got 1. I got 2. Matt, try. I got 3. Is that a vote, Matt? You're pointing a pencil up and you twitch it. No? 2 says false. Sam, where are you going with? Oh, you voted true? Kai, who'd you vote?
Rookie mistakes.
You don't know yet. Okay. Manchen, what?
The two forces can be equal as long as you start out one.
I agree with his first sentence that they can be equal. I disagree with his explanation of how they can be equal. Because he's way overcomplicating it. How could tension equal mg? if you're moving upwards, this is why I said moving upwards. I didn't say accelerating upwards. I said moving upwards. If you're moving upwards at a constant speed, well, then when you set up your winner minus loser, what would A be if you're at a constant speed, Jack? What's A exactly as a number if you're at a constant speed? What's M times 0? What's anything times 0? And so you would end up just with tension exactly equaling 2,000. Now I want to bring that back. Is that all right? Have I convinced the 4 of you that voted for true? Yes? All right.
Jack isn't convinced.
Follow-up question then. For a rock moving upwards, is it ever possible for tension to be less than the weight of the rock? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So you're either going to say, yes, it is possible for tension to be smaller than the weight of the rock if the rock is moving upwards. Or you'll say, no, it's moving upwards. It's got to be equal or bigger. Who says, yes, it is possible for it to be smaller? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who says, no, Duick, we just proved it's got to be bigger or the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Kai, did you vote?
This one better. I'll explain this one better. It could be going upwards but decelerating downwards.
Almost.
Oh.
If you're decelerating downwards, which way are you technically accelerating if you're decelerating downwards? No, you put a double negative in there accidentally. If you're moving upwards but decelerating, stop. That's good. Or if you're moving upwards but accelerating downwards, stop. But decelerating and downwards, that's double plus ungood, right? That's a double negative. So moving up, but you know what? Let's remove the physics speak. Slowing down. Slowing down. If you're slowing down, which way are you accelerating? Down. Which way must the winning force be? Down. Which means in my equation, mg would have to be bigger than tension. Yes? Okay. There's some good depth in Newton's laws there. Little technical comment, and I think I said this last year as well. So in example 5, if it's accelerating down, we have two choices. We could let down be negative always and up be positive always. Or we could just let the winner be positive. We're going to let the winner be positive because although letting up be positive always works great for single mass one-dimensional problems, as soon as we bring in 2 dimensions with more than one mass, you'll have some stuff moving right, which is positive, while something else is accelerating down, which is negative, and it's the same question. Winner's going to be whatever makes our math easier. So this big little long paragraph is me saying, again, look, this unit, you don't need to put a negative in for the 9.8. That will take care of itself. You just need to decide ahead of time which way you're going to let be winner. And what you're really saying is, that's the positive direction because it makes the math easier. Is that okay, Grace? Okay. We have one of my favorite thought puzzles of all time. Your homework is to partly study for the test, but in my mind, kind of reviewing from last year, you can try number 1. You could try number 2. What we're going to start to do more and more in Physics 12, which I didn't do much of in Physics 11, is we're going to give you situations like question 3 where there are no numbers, only variables. If you want to, you can make up numbers and see if you can figure out what the pattern is, or you can do these purely algebraically. It's really up to you. But you can try number 3. 4 is good. 5 is good. 6 is good. 7 is good. Skipping 8. Skipping 9. Skipping 10, but 11 is good. 12 is just conceptual, but that's good. 13 is good, 14 is good, 15 is good. Those are mostly conceptual. Read the question. You don't need to show any work for those. Let me pause.